Hello, hello. Okay, let's go. Let's go. Again, this is good morning. All right. So, good
Good morning,
morning.
Professor.
Oh, and even voice. Yes.
Good morning, Professor.
Oh, even voice. Yes. Excellent. I love it. Thank you. And am I saying it right? Stacy. Wait, is that Stacy? Am I saying it right?
Yes, Stacy.
Okay. Thank you, Stacy. That's awesome. And thank you. I think that was Sydney. I'm not sure with the voice.
It
Um,
was me, Loini.
Yes. Awesome. Good morning. Good morning. I'm working on my pacing here. Okay. And good morning. And for those of you who don't know, this won't take as much time each time, but it does take some time. I'm just saying good morning to everybody I see visually first, which includes Tree and Sharon. Wait, and I'm getting to the chat, and there's more people coming in. Sorry. And I know this. I just can't believe I'm trying all the different views. Oh, and there's Loani. And thank you for being so early. I know you were super early. Sorry to keep you waiting. These views, I can't believe they don't put you in the seats. I'm gonna keep trying these views until I find one where they put you guys in the seat. Or on anybody's side, on your side, do you see yourselves in these seats or no? Like, okay, anyway.
No,
No, it's so silly.
no.
That's like defeats the whole purpose, doesn't it? Okay. But good morning, Lena. Good morning, Sinead. Good morning, Sydney. And thank you, Sinead, for the back and forth. Got it. And yes, the answer is yes to your question. Of course, of course. Good morning, Tree. Good morning, Pushpita, whose name I think I'm still not quite pronouncing right. You're going to tell me again. Sorry.
Oh,
Manpreet.
you're good. It's
Oh,
correct.
it is. Oh, thank you. And thank you for the voice.
Of
Oh,
course.
thank you. All right. Awesome. All right. Um, and it's clear to you guys how to find these portals where like there's a portal for using voice, right? I think it's called Speak Softly. Or Forever Hold Your Chat, and you just remind me that you said that, blah blah. I think you guys get it. But if you don't, let me know. You get points for this. Okay, Monpreet, good morning. Fabricio, good morning. Emily, good morning. Tree. Oh, we do. Oh, we don't. Right. Got it. Thank you for answering my question. There's a portal for that too. Good morning, Erica. Good morning, Alice. Good morning, Eric. Welcome back. Um, Okay, wait. Oh, there's more people coming. Sorry. Okay. And I will switch the view. I know the view is not really helpful once we get going, but it is sort of cool how they put the board in the background there, though. I do like that. Okay. Who else? Isabel, good morning. Awesome. Okay, we're gonna start in a second. I mean, we are starting, but we're gonna start doing the physics. Um, yes, there's the physics that we're gonna start. What was I gonna say? Well, right. Okay. Okay. We're going to, and good morning, Munera. Thank you. Awesome. Okay. So I think, again, just stop me at any moment, especially those of you, this class is mostly, I mean, it's all remote, obviously. So all these like ways of participating remotely sort of matter here. The more you can make this class yours, the better for all of us. Really? And there's already a thing in chat. Hang on 1 second. Okay. Thank you. Got it. There's only one person in the chat right now, so you know who you are. I get it. Thank you. Oh, and good morning, Sarah. Yeah, and the whole email thing is crazy. They just changed all that. I can't believe how many emails. By the way, if any of you sent me an email in the last week, I I'm just getting them now and just realizing now. Anyway, whatever. But okay, yes, email is crazy right now. The migration. Um, what was I just going to say? We're going to start, but there was something. But just, yeah, stop me anytime. If, again, I think two of the most important portals really are one that, in terms of game participation points, one that's called Please Go Forward and one that's called Please Go Back. 'Cause you know what because you'll see, like, it's very helpful if you just privately and respectfully ever say, like, we get it, please move on, or we only have 15 minutes left. Or you say, wait, no, I still don't get how this works with the portals. You can tell me. Okay, but I think you do. So the goal of today, okay, I'm going to share screen. The goal of today, bear with me a second, is to start. I'm going to start walking you through just the first question, maybe the first two questions of the physics, the proper problem solving physics homework that is due a week. That's due on Tuesday, right, of next week. And I'm going to quickly screenshot just so you know exactly what I'm talking about. Bear with me for a second. Also for the sake of the recording, whatever. Where'd it go? Where'd it go? Where'd it go? Hold on one second. Oh, no, no, sorry. Right. Okay. So we are right. So this is what's due on Tuesday. Right? Um, this is, the first of several proper problems to be solved for practice in this course, practice for your exams, and practice for future life in scientific research and physics, etc. Um, so what I'm gonna do in a moment is switch screens and start walking you through what I'm expecting you to do as a student to hand in a solution to this. In other words, I'm going to do the first question right here for you. I might even do the second. When it's time for you to turn in the homework for this coming Tuesday, you're still going to redo question one. I will have already given you the answer, but part of what I'm trying to get across right now is it's so not just about the final answer. And even though here I'm literally going to give you step by step the solution, still you're going to make sure you understand the solution I just gave you. I think you will. I don't think the first question is particularly um, stressful. So you're going to make sure you understand what I did, and then you're going to do it your way. Some of your words will be the same as mine. Of course, some of your equations will be the same as mine. But if you really understand what I've done, no matter how straightforward or sophisticated it might seem to you, if you really understand what I will have done in this class, you'll be able to make it look like yours. You'll make it clear that this is your handwriting, your choice of colors, your style of putting equation in the center and putting some English on the side or whatever, and the easier you think the question is, the more you can practice dragging out the explanation, saying things that you might not think are necessary because they might be obvious to you, but you're going to drag it out and really show me that you get it, right? And this is all practice for the exam, which, as I think you've heard, at least up until, for every single semester since COVID, all the exams have been take home and open world exams. So it's not about just like writing the answers. It's about showing that you really have assimilated what's going on. So the homework is where you practice doing that. So I'm going to show you now what I mean by that. And even though I'm like spitting it at you, you're still going to go home and show that you get it, right? And then the rest of the questions you'll do on your own in the same fashion, right, and produce for me for this Tuesday. And there's more to be said. I can't remember, I'll say more exactly about like the points and the grading implications and all of that. But the main focus for today is me showing you the methods and procedures and systems for doing these problems and handing them in according to my expectations. Last thing, all of this is also the assumption here. I mean, there is a textbook that is recommended in the syllabus. It's totally optional. It's good, so you have a resource that where I'm getting all my material and so that you're not just relying on me, et cetera, but it's totally optional. You can get any edition. You can get, I can't tell you to break the law, but if you can get an edition in your native language and it's an old PDF, like whatever, I don't need you to spend money on this textbook is what I'm saying. But I also know that you can go for any time you do these homeworks and possibly even the exams. But anytime you do these homeworks, it's understood that you should be getting whatever help you can, however you can, from all primarily from one another. You can work together. You should work together, but you can also, ask tutors. You can also go to online resources for any kind of help you want to get through these homeworks, because often I'm asking you to think about things before I've even explained them in the room. I explain them afterwards. So it's understood that you can go out and consult any resources you want to try to work your way through these homeworks. But the point is that by the time you're writing something down, by the time you write it down, you understand it. And you're only writing down things that you understand. Therefore, you're explaining them to show that you understand. Okay, I think that's all. And so you can make mistakes and take risks at first, and then you get further revisions to improve. I think this is all clear, but I just want to, so I'm gonna now show you how to do this homework. So I'm gonna switch back the screens. And again, this is meant to be a transition from Physics 203 to 204. In other words, the early questions on the sheet are kind of reviewish. Certainly, if you have notes from Physics 203, have them with you when you do this. But then by the time it gets to question 9, it's hard. It's the new material. It's not expected that you already know it. Question 9 is not an exercise. It pushes you into the new realm. So you've got questions 1 through 8 to get the motor running and set everything up you need to try your best at question 9. Okay, so I'm going to start now. I'm going to switch screens. You can stop me anytime again, but I'm going to switch screens. Bear with me. Okay, so we're back to this. And these acronyms right here on the, and this will be the case for those of you who have never had me before. Every day, the first page of the board will always be sort of a preview of whatever big equation or big concept is coming that class. It's kind of like an agenda. So you won't necessarily, so you copy it down in your notes, but you won't necessarily know what I mean on the first page. Is to show you where we're trying to get to. So what these are the acronyms for the 5 steps of the 5-step method that I'm about to show you, and is also in the tools section of Google Classroom. And SSD means self-sufficient document. You put all these steps together, and what you get is the gold standard self-sufficient document that you're trying to get. So, okay, all right, I'm going to switch the view on the screen now to something normal because I think this is maybe a little bit distracting. Okay. All right, so just some notes on this. I think I've mentioned this before, but just to be clear, yes. The whole idea is I'm saying the homework is due 9:25, excuse me, yeah, 9:25 on Tuesday, right? That means that means you're turning it in before we've gone over it. Right? It's like a flipped classroom. You're trying your best to do these questions before I've explained them. So you're doing your best. So by 9:25 Tuesday, you hand in a thorough, honest attempt at a first draft. You follow the prep per formats, you show the steps, you show that it's a self-sufficient document. And as long as you get in a first draft that's appropriate before 9:25, then I need to be clear, then you will have infinite opportunities to do infinite revisions if you want, according to whatever comments I made, according to whatever feedback you get. You can keep revising and uploading until you get a perfect score. This is true of all the homeworks. As long as you get the first draft in and it's thorough by the time that it's due, you can just then don't stress that you made mistakes or certain things were left out or whatever. As long as you get more than half the points right away, that is a signal that you got in and on time, and you can now get all the points, whether or not you got a ton of feedback on the first draft. Often, or at least in the past, often people don't get a lot of feedback on the first draft because I go over it in class, and a lot of it becomes obvious what you need to do. So you go back and you submit a second draft. That's when I start looking at things really closely, maybe. But also, last thing on this. It's important to be able to take risks and make many attempts and never think that your first attempt is your only attempt, blah, blah, blah. Therefore, whenever I say do revisions or submit further drafts, what I mean is always, leave up the old drafts in the Google Classroom assignment portal. This is also true for all of the game portals. Like if you show video today and then you send a screenshot that you showed video today and you send it to the video portal so you get points, then tomorrow, next class, you can do that again, but you could do the exact same thing again and get more points, but leave up the old screenshot so that, by the fifth time you've done this, I can just look up and count. Oh, there's 5 screenshots of there. I know she showed video 5 times. So we both make sure, okay, she should have a total of 5 times whatever the point value is. Always leave everything up. How do you leave everything up in Google Classroom? Before you attach a new thing, you hit the button called unsubmit. You hit, it won't erase anything. It won't remove your old draft. It won't change your grade. You hit unsubmit, you attach a new document, then you hit submit again. That will automatically notify me to look for new stuff from you. And then I can update and improve the grade. I hope that's clear. Again, if it's not, stop me or text me or whatever. But that's the point for all. Okay, I think it's clear. All right, I'm going to go on because I want to get to this physics, obviously. Yeah, so that's what this board says. Again, you'll get the PDF of all this, but just keep up each draft each time, press unsubmit. Okay, I just said that. Okay, so here we go, finally. All right, so here we go. We're now pretending that we're you, like turning in this first homework to me. So notice, first of all, I'm like on a blank sheet, right? I've taken out blank sheets of paper. I've got a pencil, right? Or maybe I'm on a tablet and I've got a stylus, but really, maybe I'm typing on a fresh blank guide. But if you're going to type, like you should talk to me personally. Like, let's make sure you really know what you're doing if you're typing out these homeworks, because I recommend it only really for certain people. But anyway, so you're on a blank piece of paper and you're writing, and it says like homework 1A thing on a spring, okay, as a title, maybe even ideally the name. But now, right away, so this is what I mean already by self-sufficient document. Notice there's nothing of my original sheets is here. This is important. It seems silly, but it's important. This is like a blue book. You're not attaching my original sheets and you're not copying and pasting anything from my original sheets. And you're definitely not trying to squeeze your responses like into between the lines on my original sheets. It's a bad idea on many levels. So notice there's no reference to my original sheets here at all. That's part of what I mean by self-sufficient document. Question in the chat. Just a copy of it. I'm looking in the chat. One second. Oh, yeah. Nice. Oh, wow. I don't know if this is legal what we're doing here, but yes, that is the book. Okay, wait. I should probably not get involved in this, but that's awesome, Luani. I think that's all. That's definitely multiplayer co-op. I might have to ignore this because I'm not sure that, but yeah, but good. Yay. That's multiplayer co-op. She's right. Yeah, I'm gonna walk away. But yes, okay. Sorry. Yes, awesome. Okay, so this is a self-sufficient document. There's no reference, and you're going to see in a minute. I screen shared once so that you all could see, the original problem, or you could see it if you're watching this on a recording. But from here on in, everything I'm going to say about this problem, none of us, hopefully I'm drawing this out in a way that none of us should have to be looking at the original problem to have this discussion. That's the key. That's part of your standard. Like when you submit the homework to me, you're trying to give me something that I don't have to be consulting more than one piece of paper. I should just be able to read what you're doing to follow it. Or conversely, if you're giving it to a tutor to help you, you shouldn't have to give them any other materials. They should just be looking at it and be like, oh, I get this physics. Oh, I see what's going on. Oh, I don't think you did this right here or whatever. Or if you were submitting this to a journal, like whatever, you want to go high or you want to, whatever your standard is, it's standing on its own. You see what I'm saying? Okay, so step 1 of the 5-step method. Step 1, DFP stands for diagram and fact pattern. The first thing you do every time of every physics problem, definitely including exams, is you provide a diagram and fact pattern. Sometimes the original problem gave you a diagram like I did on this one. Sometimes, like homework 2, there are not original diagrams. Either way, you're providing a diagram. Might it look very similar to the one that I made? Might it be based on the one I made? Sure, sure, but it's still yours. You're making it, you're not copying and pasting it. Can you use a computer to make diagrams? Sure. If you're good at that sort of thing, that's lovely. If you want to use a computer to make pictures, or if you want to use AI to make the picture, Quark bless America. Like that's a good use of AI as far as I'm concerned. But now what's the standard of the diagram? Like what are you looking for in this diagram? Okay, two things. Number one, the purpose of a diagram is to right away set the stage that although math is the language of physics, math is not the topic. The topic is physics. What makes physics physics is it's situations that exist in space and time. So number one, the diagram orients us to space and time. It makes it a physics problem. Okay, that's number one. Number two, far maybe more directly important is we're going to get math will become the language of this. The harder the problems get, the more there's going to be mathematical computations to do the solution, right? Algebra, trigonometry, calculus, etc. Well, there's going to be a bunch of constants and variables all throughout the math, a bunch of letters. The letters don't mean anything in the math unless they've been defined. A reader doesn't know what X stands for. I mean, maybe X is kind of common, but like as we get more and more sophisticated, you're going to be using letters that no one knows what they mean in if they don't already, in when they sit down to look at your work. So what the diagram does is it defines all the letters by making them labels of the diagram. So the key of the diagram really, really is the labels. Every letter that's ever going to appear in the math, in the subsequent steps, has to appear first as a label in your diagram. That's really the point of the diagram. And again, this is part of what I mean by self-sufficient document. If we start seeing letters in the step 4 that we have not been established early on, it doesn't make any sense. We don't know how to read it. And quite frankly, also often that's a signal that someone just pulled a bunch of stuff from AI without like learning from it and just pulled it. And it's just like there sitting without context. That's not a self-sufficient document, right? So, is that? Oh my God. Okay. I just downloaded that entire. Okay. Okay. So we label the diagram. So here's my, sorry. And third purpose of the diagram. And again, everything I'm saying now that's like not written here, hopefully is helpful to you. If you're taking notes and you ever write down anything that I say, but that's not written on my board, screenshot it and send it to me as an example of good note taking. So what I mean by that is purpose 3 of the diagram is to establish coordinate system, to make choices that are going to be used throughout the physics problem that make a huge difference. For example, here you'll notice I'm choosing in the blue picture, I'm choosing to say everything to the right is positive, everything to the left is negative. It's only a one-dimensional problem, so it doesn't get more complicated than that. But that is still going to make a difference in all of my answers, as you'll see. So I'm choosing to call right positive, and left negative. What that really means in the context of this is I'm choosing to say that when the spring is extended, we're calling that the positive. When it's extended away from equilibrium, we're calling that positive. And when it's compressed in from equilibrium, we're calling that negative. Okay, I could have chosen the other way. But whatever I choose, I'm telling you in the diagram. Notice, I'm about to go on, I promise, but also notice this subtlety that will become more important in Physics 204. The labels I'm talking about are indeed letters. Like M is labeled in the diagram. K, the stiffness of the spring, is labeled in the diagram. X naught is labeled. Now it happens in this problem that you're given numerical values for those letters. Sometimes that's true. The reality is as you get more and more advanced in physics and as our problems get more sophisticated, we have fewer and fewer numerical values because more and more we're really just trying to solve problems in general. We're more and more just trying to say, like, how does a mass on a spring work, regardless of what specific mass you happen to be looking at? So the numbers are not really the issue. The issue is the letters. But if you're trying to get numerical answers, you might have values. So this is what I mean by fact pattern. Notice that my diagram, the labels are letters, and then underneath I have like this little legend or whatever. I say, okay, in the handwriting is kind of, sorry, faint, but it says like, okay, in this case, K happens to be 200 newtons per meter. Mass happens to be 0.3 kilograms. X naught, the initial position, happens to be 15 centimeters, right? That's what I mean by fact pattern. So you try to follow that model. Every letter that you're ever going to use is established as a label in your diagram. Then, if there's numerical equivalences, you then sort of outline them below. And any other facts that might be important, you're putting below. So diagram and fact pattern. That is what I mean by DFP, step one. That you'll notice is sort of like a big part of the grading rubric. If you ever see DFP again, that's what I mean. When you're doing your homework, should you do this? Yes. Should you, when you're doing an exam, should you do this? Yes. Should you literally like label it like step one? Sure. I mean, make it as easy on the reader as possible. Say like step one. Now, not everybody in the world knows what DFP is. So you might want to say step one, diagram and fact pattern, or you might want to set up a little legend in your homework, like from now on, DFP stands for diagram and fact pattern, right? Whatever. Don't assume that everybody in the world uses the exact same steps that I do, but everybody in the world who's educated and does physics will totally be able to follow the purpose of these steps, as they are universally understandable if you say what they are. Okay, so yes, please label your steps. It will help us both. All right, so that's step one. Sorry, I see something in the chat. But okay, that is step one, diagram and fact pattern, DFP. Now, great question from Alice, and thank you for going public. And you should definitely submit for points for this question. Do we need to provide a frame of reference for every problem that we solve? It's such a great question. I mean, the fast answer is yes. Sometimes it's as simple as what is positive and what is negative, but sometimes it's more sophisticated than that. Yes. And I know I didn't have you in class last semester, but what I really secretly believe, even though every professor does this differently, really the point of Physics 203 underneath it all is Galileo's principle of relativity. There's a million different ways of saying it. Your professor might have not even said that. That's fine. But really, the point of physics, what differentiates physics from math, is the choices that we make for how we set up the math. The math turns out to actually not be the hard part of physics. The hard part is setting things up to know what math to do. And that comes from making choices about frame of reference. So my not so short, but yes, yes, the answer is yes. I mean, I could go on for, I mean, maybe there's some exceptions to that, but when in doubt, if at all possible, yes, please. Okay, good question. Oh, also, wait, there's another question. Do we need Oh, okay. Okay. Now, do we need to provide, great question. Do we need to provide conditions for a formula that we may use? Okay. Well, I guess the fast answer to that is also yes. I think we're going to get to that a little bit. The distinction between the conditions and the equations and stuff like that sort of will come more clear in step three. I mean, so yes, you have to provide conditions. You'll also find I don't love the word formula, to be honest. I mean, I understand why you're using it, and I appreciate the question. Your question's really going to be, I think, more extensively answered when I get to step three. So I'll leave it at that for the moment. I mean, the quick answer is yes. But remind me if I don't get, when I get to step three, I want to say more about what I think you mean, and also sort of, I want to say more about conditions, but also about like formulas and what they are. Okay. Oh my God. Okay, Sarah, great. Wow. Great. If and only if statements. If by that, great point, Sarah. If or put another way, like triple equal signs as opposed to double equal signs. Yeah, if and only if statements only, if and only if statements. That's really good. I'm not 100% sure. I love that. I think Sarah's question about if and only if statements is also very much about step three, which if you're both subtly trying to tell me to move it along, doggies, I will. So I'll move it along. I think what they're both talking about really will be best addressed in step three. But right now, I'm saying for step one, you're presenting the facts of the particular problem. You're giving me the picture, and basically you're copying from the sheet, but you are going to copy from the sheet. Like you're not going to copy paste. You're going to transfer because you're showing that you know what the situation is. You know all of the important details and nothing extra. Okay, I'm going to keep going. So that's step one. Now, step two, and again, this is, I'm telling, this is for this homework, but this is for always. I think it's clear to everybody. And I am watching the time. Okay, it's 9:55. Now, step two is WIQ, which means what is the question? So, and that is such an important, oh my God, I could tell you stories. It seems like such an obvious, like, why are you wasting your time? Like, we already know the question. But the harder physics gets, the more people find themselves either unconsciously or consciously looking at physics situations and going, I don't even know what this thing is even asking. Or worse, they don't say that to themselves. They start diving in and trying to answer, but they're all over the place or having a hard time or hitting that classic physics or science student wall going, I have no idea what to do. And which is never actually as true as it feels. But whenever you feel, but believe me, I have felt it many, many times. Whenever you feel I have no idea what to do, part of what you really mean, well, part of what I really mean when I say I have no idea what to do is I don't really even know what I'm supposed to be trying to do. Like I don't even know what the question is. So it's really also, well, whatever. And again, this is not just if you don't know what's going on. When you do know what's going on, I mean, I cannot tell you the number of times my PhD dissertation bounced back to me in early stages because I had written like 85 pages and I was like, oh, it's super advanced. I thought I was like, solving the universe. And my advisor just kept sending it back to me going like, okay, but what are you even saying? Like, what is even the research question? You have to tell us what the question is before you start. Like, we don't know what you're talking about. Right? So you got to say what the question is. Now that means you take the question and you distill it down to its essence. You see, I use way too many words already. It's driving some of you crazy already. Even in my sheets, I use too many words. Don't be me. You want to distill the question down to its fundamental elements and nothing more. That means you can and maybe should even be symbolic. Don't use my words. You saw the first, so question one of the sheet was at when the mass is initially held in place, what is the force exerted on it by the spring? Now, truth told, I actually am not using too many words if I'm using English. Really, if I use any fewer words, I really wouldn't be precisely stating the situation. But English is clunky that way. That's why we use math to do physics. I'm asking you in English this question. Now, once you get it, you can write down something straightforward like at x equals x naught, f equals question mark. That's what I'm looking for. Okay. And if you just write all the same words I just wrote, it shows me that you're reading the sheet. It doesn't necessarily show me that you understand what the sheet is asking you to do. Okay. So you write down what the question is for step two. So step one, here's the situation. Step two, what's the question? The question is at the initial position of displacement from equilibrium, what force is being, or what force magnitude is being exerted by the spring on the mass? That is step two. What is the question? I'm looking. Oh, she did. Oh, great. Oh, sorry. I'm looking in the chat. I'm so psyched. Oh, great. That's what. Oh, no. And you're not confusing me. Oh, this is great. I'm actually really touched and moved. I wasn't sure whether Professor Talley had been emphasizing this. I mean, great. I'm so thrilled. I mean, of course, a long time ago, anyway, I'm thrilled. But of course, we all have slightly different styles. So wait, I'm looking. She enforced. I'm so glad she enforced. Great. All right. So in a way, I'm wasting some of your. I kind of thought this was new to many of you. If it's not, I'll go a little faster. But also, it's just good for you to know exactly what I'm looking for. Blah. And you'll see too. You'll see when you sit down to do this homework. There's a grading rubric already in the portal. Did not do that last semester. For those of you who do know me. So you should open, and it's not it'll be improved each assignment. It's not a perfect rubric, but um, feel free to open it up before we even get going, so you know what we're looking for here. So the if and only if thing, yeah. Oh, that's great that she did that. Yeah, I tend to think of is that a requirement? That is if and only if is a requirement. If I'm understanding you correctly, it's certainly a requirement, I think, for step three. Um, I'll get back to that, but no, this is great. Keep the chat going, all of you. All right, so that's step two. What is the question? But now I know you know. So, all right. Um, and again, for any of you who did not come from Professor Talley or me, this is under tools in Google Classroom. There's one sheeter with these acronyms defined, and then there's a couple of examples. One from a student and one like a lot, whatever that you can look at in tools. Okay, anyway, now step three, where we get into issues. Step three is where things, you really have to start thinking and it becomes more and more important and maybe more subtle as problems get harder. Step three is GDP, general definitions and principles. Now, this is what I think these guys mean in the chat. Like, this is where we would start writing down things that I would call triple equal signs often triple equal signs as opposed to double equal signs, or if and only if statements, right? These are statements of universal truth. These are statements that are true about physics even before this problem was introduced, right? So let me slow down for a second, even if you've heard this before, because this is where I tend to be a harsh grader in the homework and the tests. Um, I tend to be picky in step three. So let me back up for a second. So the example of what you'd write down for step three in this case for this question would probably be what says up here, according to Hooke's law, for a well-behaved spring, F equals negative kx. The force exerted by the edge of the spring onto some attached mass is directly proportional to the displacement of that mass from equilibrium and is directed oppositely to that mass's displacement from equilibrium. Like, I'm going to describe that in principle. You all know that from physics one. If you don't, you look back at your notes or look up in Khan Academy or in the textbook or whatever. I'm going to try to briefly explain it again in a second for review, but it is under, and I've even provided a little graph here to show what I think I mean by that law. I'm just show, and I'll explain that graph in a second. But notice, this is a general definition or principle, GDP. This is something that I think has been established already in physics at this point. Something that is either so self-evident because it's a definition, like, right, like that it can't, it's either, I mean, it's already been established as a definition, and as a definition, it can't be argued, right? Because it's just the way we use language, or it's already been established as a law, or if it's slightly more sophisticated or derived than that, it's been derived already, like in the last class or earlier in this class. It's a known truth from the context of physicists at this level. That's what we're putting down for step three, right? What I mean is, we all know since seventh grade, when you're trying to solve a problem, you're supposed to like first write down what you know and then, try to figure out what you don't know, something like that. What I'm trying to say is there's really two different types of knowns, or at least two different types of knowns. There's what you know about this particular situation. That's step one. And then there's what you know about the world that will help you with this situation. And whatever you know about the world, you had to know before you got to this situation. Otherwise, it wouldn't help with this situation. That's step three. So step three, you got to write down things that have already been established that are somewhat more self-evident and clear than the solution to this problem. But that doesn't mean that they're obvious. It means they're already established and somewhat clear. So you do provide a little bit of context for them. Like here, I'm writing F equals negative kx. What I'm really saying is that the relationship between force and displacement on a spring is linear. So I'm providing a little graph of the straight line to show you what I mean by that, right? It's not a proof, but it is a little bit of an explanation of context, right? This is what we mean by Hooke's law. Notice, if you don't remember Hooke's law, or for a quick review, we're saying that the farther you stretch out a mass on a spring, the harder the spring pulls on it to bring it back to equilibrium. We're saying that if the mass is on the right side of equilibrium, the force will pull to the left. If the mass is on the left, if the mass is already in a position that we call negative, the spring is going to pull to the right. So the spring pulls in the opposite direction of wherever the mass is. That's called a restoring force. That's what that negative sign in the law means, that the force is always directed oppositely to the region of displacement. That's why we labeled our coordinate system at the beginning, so we can get our pluses and minus signs straight. So the negative doesn't mean that you always get a negative answer. It means you get, for force, it means you get an answer that is the opposite of whatever displacement is. Okay, that's number one. But so you get a straight line, if you make this graph of force as a dependent variable, displacement as an independent variable, you get a straight line in the fourth quadrant. Straight meaning the slope is always the same. What's the slope? The rise over the run. The rise is change in force. The run is change in position. So the slope is known as this letter we call K, or the negative of the slope, whatever. The magnitude of the slope is what we call K. Why? That's how much force the spring exerts per each meter of displacement. So for any given spring, the K is one number. But for one spring, it might be a bigger number than for another spring. What would that mean? It would mean a steeper line, i.e., more force per displacement, i.e., a stiffer or stronger spring. So K is always measured in newtons per meter. It's the stiffness or the strength of a given spring. Any part of what I just said, if it made sense to you, you would distill it down to its essence and give just a little brief gesture toward that in your step 3 background. The fundamental step 3 here is F equals negative kx. And then I'm just giving a little background or a little context so that we understand what we mean by F equals negative kx from here on in. And notice, like K and X were defined, up in the diagram. Last thing, what I'm really saying, and then I'll go on. And I'll go on. Oh yeah, last two. Well, okay. So this is where you put known equations, right? This is where you start writing equations that you're going to use to solve the problem. Choosing those equations is often the difficult part for physics students. Like physics students think, including me, definitely including me, we go into physics being sort of scared of the math, hearing that the math is hard in physics. It turns out for 9 out of 10 physics students, the math ends up being what we just rely on. The math, as far as computations, doesn't end up often being the hard part. The hard part is, how do you begin these problems? How do you set up? Which math do you use? Which equations do you use? That's often what people will come to office hours and stuff for help with. What I'm telling you is, if you properly set up step 1 and step 2, you'll have an easier time by the time you get to step 3, knowing what to choose for to do the rest of the problem. And yes, it's a question of what equations are you going to write down to use the rest of the problem. The more self-evidently true or fundamentally true they seem, the safer they are. Why I don't like the word formulas. I'm not criticizing you for using it. I'm actually glad you used it to bring up this conversation. It's a legitimate word. But why I prefer to use other words is, the thing about formulas is formulas tend to suggest some kind of like recipe that we memorize, that we don't really know why it works or really care why it works or know where it came from or anything, but we know that it works. So we sort of memorize it and then we plug things into it. And that's all fine. Like, we all do that to some extent. But the thing is, once you're looking for formulas, you're kind of already admitting to yourself that you're giving up on trying to make sense out of the situation. And it becomes a little bit of a desperate scramble and a little bit of a like hope and dumb luck kind of exchange. The idea here is not to, so, and the flip side is what I'm saying is, here in step 3, where I'm really looking for is, does a person write down principles, laws, truths that have been established in this class that we know why they make sense, and they're giving me a quick reminder why they make sense, or if it's, or they make sense out of it in the solution itself. Unfortunately, if you're not, the pro tip is, when I see formulas that are statements that are true but just came from the web, that do work to solve this problem, but we've never seen before, or we don't know why they're true, but they're just like workable formulas. When they're written down here, that's a signal to me that someone is not understanding what's going on and using web resources in the wrong way. I mean, I'll move on. I think we all know what I'm saying here. Like, you want to sort of avoid formulas. You want to only write down equations that make sense, which and if it's a new equation that you're not even sure if we've said before, but you now can see how it makes sense because you've read a bunch of stuff online and it seems reasonable. You just don't remember it, but it seems to make sense. Well, then show me how it makes sense here. Like, always bring it back to fundamental principles, ifs and only ifs, like Sarah and Alice were saying. Okay, I'll move on, but this is where I think you get my point. We're not introducing fresh new knowledge here. That's what we're introducing in step one. Step three, we're uncovering old knowledge that we think will be helpful here. All right, I'm going to, okay. So in this case, it would be f equals negative kx, and then maybe a little graph or something like that. Oh, okay. Step four. Now we get into the work, like what you would traditionally consider showing your work for a problem. Now we're up to step four now. PAW stands for particular application and work. This is where you do the computation, where you plug in the values, where you track units and scientific notation if applicable. And this is where I'm going to tell you, even though I've got to put this more strongly into the grading rubric, I'm telling you right now, this is where you want to have English as well. Now, there's not much to do in this particular problem, in this first exercise that we're doing. But the more sophisticated they get, the more you're going to want to intersperse lines of trigonometry or lines of calculus or lines of algebra. You're going to want to intersperse those lines with English commentary in your style. Either go like math, then English, math, then English, math, then English, or like math in the center with English around it, something. But you're walking me through a process here. In particular application and work. And so it starts with, I generally will start step four with a word like here, because what I'm saying is, all right, what we already said in step three is like F in general, in the universe, F equals negative kx. But now here, now I'm going to zoom down from the universe to this particular problem. Here in this particular problem, K happens to have the value of 200 newtons per meter. X naught happens to have the value of 0.15 meters. So I'm just changing the screen for, hold on. Right. So I plug in and I track my units and I cancel out the meters, right? So, and there's not much else to do here, but I multiply in 200.15 meters, and that's my work. For maybe I would even add a line of English, but say I crossed out some term because it was equal to zero, I would say why, right? So this is like the narrative here, step four. I tend to be a little bit picky here as well. Now I'm about to move to step five, but let me, again, warning. Let me back up for a second. I mean, again, and I realize I'm glad you already got this with Professor. Actually, I'm thrilled that you've already gotten this with Professor Talley. So this shouldn't be, so this is like just reinforcement today. But I also know, I know from experience, people hate doing this at the beginning. I mean, I know this draw, especially when the exercises are somewhat, a lot of you could get this answer. The answer for question one, especially if you know that f equals negative kx. Of course, a lot of you can just do this in your head. I know that. But I'm asking you not to just write down the answer that you got in your head. I'm asking you to drag it out and show all these steps, because what I'm claiming to you is that even if you think you just got it in your head instantaneously, that's because you're really smart and good. Seriously, if you just saw the answer right away in your head, it's not because you had divine inspiration and it came to you in a dream. It's because your brain went through a series of steps so quickly that it seems like it was instantaneous to you. What I'm asking you to do is, on these easy exercises, practice dragging out, slowing down the movie of your mind and seeing what steps your brain had to have got. Like, there's no way you could get the answer to this question unless you actually do know that f equals negative kx, and you have to know that k is 200 and x is 0.150, and then you multiply them together, right? Like, you had to do that. You just did it really fast. So I'm saying let's spread it out and see what steps your brain did to get to that answer, because when you get to a problem where people tend to say, I have no idea what to do. I have no idea what to do. What is this? I don't even know what he's asking, which will happen, right? And then you start either getting angry at me or upset at yourself or whatever, or at least that's what I used to do. What I'm arguing is, and then when a professor says, well, if you don't know what to do, why don't you start showing all your work, do your steps? People generally, I certainly back in the day, if I said I have no idea what to do, and then someone said, well, start writing down your steps, like show your work, I'd be like, I would, but I don't literally know what any work to do. Like, I'm telling you, I don't even know what to do. Like, I knew what to do when it was easy. I didn't have to do much. I just saw the answer. Now that it's hard, I don't know what to do. This is a curse of being smart, actually, or of being a really good student. We get used to seeing things quickly. So then when we don't see them quickly, we think we don't see them at all. What we're trying to train ourselves as physicists here is what it's like to see things slowly, what it's like to see things when we have to look for a while until they get into focus. So what I'm saying is, when we don't know what to do, like question 9, by the time you get to question 9, a lot of you won't know what to do. And that's not an insult. A lot of you won't know what to do to question 9, or like how to get the answer. You won't see the answer in your mind right away. But if you just follow these steps, if you do, you can do step 1, step 2, and step 3 without having any idea yet how to proceed. You're just setting a table, and you'll have a much better then when you get to step 4, when you have to actually start like solving, it'll be much more evident what to solve and how to show work if you've already done steps 1, 2, and 3, which frankly are the thing that most people skip. And conversely, even if you do step 1, 2, and 3, and even when you get to step 4, somewhere in the middle or at the beginning, you're still stuck and it doesn't solve the whole thing for you, which I think in most cases it does, you've still gotten full credit. You've gotten all the points for doing step 1, 2, and 3. So no matter what, this is a safe, the process is there to help you. It makes it harder when you're doing easy problems, or it makes it more annoying and irritating when you're doing easy problems. But the bottom line that it took me over 30 years to realize is that sometimes we're way out at sea and we need a life raft, and that secret to physics is the recognition that you can't build the life raft when you're already at sea. You can only build the life raft when you're first on land and you don't think you need one. Honestly. So that's what's happening here. When we drag out these easy questions into steps, we're giving our brain, we're training our mental muscles to have a process to rely on once we actually need it. It won't work if we haven't practiced it before the moment of need. I think you get what I'm saying. So this is step 4. We do the computation. That is much easier for having done, if we've done steps 1, 2, and 3. And then, like, I'm losing people by the dozens. It's getting really boring. Sorry. Okay. I'm totally insulted. Okay, so here's step 5. For those of you who still stayed with me, step 5, final answer circled. This is where you present a final answer. And indeed, you circle it, or you boldface it, or you highlight it, or you box it. You definitely make it clear, I am now done. This is what we were looking for. If this were a research paper for a journal, this is the finding. This links us back to step 2. This closes the loop on what we introduced in step 2, right? And we're telling everybody, this isn't just random information. This is the point. And we phrase the final answer as a complete statement, like a complete thought, i.e. an equation. And now here we get to the condition thing that either Sarah or Alice was asking initially. Like, here's where we literally refer back to the condition of the original question. The original question was not just what's F? It was at x equals x naught, what is F? So my final statement is, well, when x equals x naught, or in this case, when x has a value of 0.15 meters, the magnitude of the measurement of the force is negative 30 newtons. It's a complete thought. My answer is not, so please notice, and this already sort of happened to somebody on the homework like the answer, even if when you circle it, the answer isn't 30 newtons or negative 30 newtons. The answer is that F equals negative 30 newtons at X equals 0.15 meters. Am I being picky? Yes. I don't know what to, yes, but that's the deal. The answer answers the question, and it's a thought. It could stay, it's all about self-sufficiency. It could stand on its own as a finding. Um, okay, so that's the final answer, complete statement with the units and the condition that refers back to the original question. That's a final answer circled. Okay, we're going to pause for a second. So that's, okay, that's a lot. Uh, I apologize, but that's what I'm looking. Your version of that is what I'm looking for step one. Excuse me, no, for question one of the homework. Those 5 steps in that way. I've now done it for you, so you don't have to read. But it's almost a test. You'll see that by redoing this your way, since hopefully you'll be confident and almost bored, you'll be able to find a way to show me that you get this, that you're not just literally copying and pasting what I just did. And then you'll follow the model for the rest of the questions. I'm going to go on. We still, well, okay, I'm going to pause for a second. Is that, can I just, are there any questions? Okay, can I get electronic hand? I'm guessing I'm going too slow. Again, I was sort of assuming, I knew I
No, we
didn't.
understand.
Great. All right, cool. Thank you. Awesome. And again, I sort of apologize. I did prepare this class with the belief that since most of you didn't have me before, that I wanted to make this super clear. Now that I realize this was emphasized with Professor Talley, I sort of apologize if it's sort of boring or redundant, but as long as it's clear, that's the goal. So thank you, Stacy, for using verse and say, and thank you, Sydney. Okay. Oh, and in particular, Sydney. Okay. And Sarah. All right, awesome. Thank you all. And why are some of the things, I guess it depends what updated version you have. Thank you, Lena. And thank you, someone else I just missed, but thank you. Awesome. All right. And Maya, great. All right. So I'm going to keep going. I'm going to keep helping you with the homework if I can. We might even end a little bit early. Never do, but I didn't say that, but maybe we'll. All right. We're going to go to question two now. Now, question two is not much harder. Of course, the questions get hard. Sorry. Thank you, Tree, for what you're saying. I appreciate your kind words. No, that's helpful. And again, no, and I'm not just fishing for that makes me happy, but also I am trying to send you all a signal. Like, of course, I like compliments, but I'm also trying to say this is your class. So, like, as you get more used to me, or as the expectations become more clear, you are definitely allowed, politely, maybe in direct chat, if you're allowed to say, like, okay, we get it. Please move on. Like, really, because I know either way, like, okay, you get it. So I'm going to go on to question two now. Couple of things now. Like, so what happens now? We move to question two. Do you have to draw and we're going to do this whole process again. I'm going to talk a little faster. Now you get it, but a couple of subtleties. What happens if you're on the second question now? Do you have to redraw the whole diagram again? No. You don't have to draw the whole diagram again. If you're still using the same diagram, but acknowledge, like, this is a recipe. Like, so I'm saying in step one, DFB, for the diagram, like, I'm labeling. I'm on question two now. Sorry, I'm on hello. I'm on question two now. So for the diagram, see above, right? I mean, that's all I have to say, but I'm acknowledging you probably need a diagram to visualize this. Well, there it is up there, right? Again, you are at all times, the standard is either, could this work as a journal article to someone who's not in the class, but who's going to learn about masses and springs? It might not be the most original journal article, but could it be explaining to someone how masses on springs work? Or could this work for a tutor who has no idea what the assignment is, who's trying to help you? Or if you're turning it to me and you want me to get this back to you faster than I got things back last semester, you want me to get it back to you fast with constructive feedback, make it as easy on me as possible. Don't expect me to be looking at other documents while I look at this. So address every need. Like you just say, I'm not going to do, the diagram is above. Okay, acknowledge. Awesome. And same thing, step three, if it's the same GDP, it isn't in this case, but if you're going to use this, and this definitely on exams, pro tip, sidebar, pro tip, on exams, whenever a hard, important new idea gets introduced on an exam, like omega, the whole idea of omega, we'll get to that. The first time in the exam that you're using omega, you're definitely going to want to spend a lot of time explaining to me that, making sure that you understand what omega is and making it clear to me how you're going to use omega, right? but then you're going to use it all throughout the exam. So the first time, go crazy, go overboard. Then for the rest of the exam, you can always say, refer back to page 2, refer back. I mean, we're not trying to be obnoxious, but we're just saying, give me a show that I can watch without having to watch the whole season. You know what I mean? Give me an episode that you get what I mean. So, all right. Oh God, every time I do that, I lose somebody. Okay, so for diagram C above, cool. Then question 2, I mean step 2, what's a question? It's a different question now. I think it is, yeah. At x equals x naught, what's A now? Like it was, what is F? Now it's what's A. Okay. Step 3, the GDP now. The GDP here, now we're gonna, we're gonna move our knowledge from force to our knowledge of acceleration. Of course, that's Newton's second law. Now, things almost could not be more fundamental than Newton's second law. Like we are assuming all of physics is kind of based on Galileo's principle and then Newton's laws of motion. So yes, it's understood that that's fair game. But let's get it right. Let's get it right. The law is the sum of the forces acting on a mass produce the acceleration of that mass. The law is down here. I mean, it's such an important law that you might not have to explain it a lot, but you certainly want to get it right and you want to use it right. I've already gotten a bunch of homeworks from other people in other sections where this was already, they were playing fast and loose already by this point. And it's like a little makes me feel funny inside as a physicist. What I'm getting at is this. First of all, it's the sum of all of the forces. That's what the law says. The sum of the forces. You could also write F net equals ma. That's legitimate. Same point. But it's not just any old F. It certainly is not that spring force equals mass times acceleration. That's not a law. The law is that the sum of all the forces equals the mass times acceleration. Okay, that's number one. Number two, it's a vector equation. Now, it may not be that big of a distinction here in this one-dimensional problem, but you will recall from Physics 203, and it will become important later. F net equals ma is true on more than one axis simultaneously yet independently. It's a vector equation. Like what it really means is the sum of the x forces equals the mass times the x acceleration, while at the same time, yet utterly independently, the sum of the y forces equals the mass times the y acceleration, and similarly with z, right? Now that's what the law, so the law is a vector equation that has either a sigma or the word net on the left side. That's important. So you write the law down as Newton's second law and say, this is Newton's second law or whatever. Now, what are we looking for in this? Well, I'll go on. So then we can get to pilot. Right. This is all like a pilot episode. Right. You treat all of this as though it's like a pilot episode. Exactly. I love it. You're totally, and you should submit for points for that. That is not only funny and helpful, but it's also showing that you're totally paying attention to me. So I appreciate it. Do you all get the fact that every time someone says anything in the chat or anytime anybody who isn't me says something, it makes this so much more livable for all of us? You know this, right? That's why you're getting points up the wazoo for, okay, you got my point. Because otherwise it's rabbit hole city for Yaverbaum. Step four, now, I'm going to now apply Newton's second law to the situation. I'm going to simplify it to the simplicity of the situation. But I'm not lying about the law when I write the law. So I say here, the problem is fully 1D. So first of all, we can just say the sum of the x forces equals the mass times the acceleration of the x direction. Like there is no y-axis or a z-axis. So I can just get rid of the vector symbols and go straight to the one axis, right? And then second of all, here, the spring force is the only force acting on the mass. Okay, so here, so the sum of all the forces in this case does just mean just the spring force. So I'm going to substitute in the spring force to the left side of this law. But I'm getting a little bit intense about this because, frankly, because what I don't want to see, what I've already seen on some homeworks from other sections, was I've seen people like in step 3 write A equals F over M. Now I know why they're saying that because like they're looking for A and they knew F. But no, that's like not a thing. Like that is not, I mean, I know I sound like I'm being really picky, but it's easier for me to be picky here where I think everybody knows what's going on so that you'll be helped for later when you're not sure what's going on. Like A does not equal F over M. That's not a law. The law is that F net equals M over N times A. And then we're applying that law here, and we're going to rearrange in a minute with algebra and in step 4 and say that A equals F over M. But now, right? So I'll do that. Like, so here, the force, in other words, what I'm also trying to get away with, I mean, get a lot of people leave physics one with a lot of people in the world and a lot of people on the web and even behind a lot of people on the web actually don't understand really how F net equals MA works. I'm sorry to say this, and therefore it affects artificial intelligence. I'm not saying this as an ethical point. I'm not saying this to shame anybody. Okay, I practiced a lot. Like I went down the hole like in January of AI, and I see the attraction, and I see the beauty of it, and I see the beauty of it for you. But I also see its limitation. So I'm not making an ethical point. I'm not saying don't use it, but I'm saying here's where to be careful. Artificial intelligence is just that. I mean, it's artificial, and it's only as intelligent as all of the resources that it's pulling from. Right now, all over the web, I know from 30 years of experience, all over the web, there are tons of resources that are misunderstanding Newton's second law. And what they think is that there's a thing called a net force that other things are equal to sometimes. That's not how it works. Like they'll think, oh, in this case, the spring force is equal to the net force. So I set them equal to each other and blah, blah, blah. Well, sometimes by accident that seems to work. So people keep believing it. But it often does not work because it's not true. What is that? Is that a timer that I should go? Oh, okay. Oh, that probably just means I'm yelling too loud. Okay. Uh, what? What name? Okay, sorry. I think my watch is telling me I'm yelling too loud. Um, uh, 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 I'm just saying what Newton's second law means, because we still care about it for this class. It means add up all of the forces acting, and together they will make the acceleration divided by the mass of some mass. So in this case, the only force acting is the spring force. So sure, you put the spring force on the left side of F net equals ma, and it will become ma. That's the procedure. And to cut to the end. So then you plug in the numbers and you get an answer, which is written here, step 5, right? The final answer is at x equals x naught, a equals negative 100 meters per second squared. Now we still have 8 minutes. I still might even let you go a little bit early because we've now gotten the answer to 2 questions, which is terrific. But a couple of things. Again, all of this is meant to not only clarify my expectations and grading expectations and all that, but also to give you pro tips for when things get harder. Honestly, what physics is really about, what we're really trying to, again, because of the existence of the web and everything, like you don't need me to give you physics information. You can find physics information on your own without me and faster and your way. What you're really learning in physics is how to get smarter as a research scientist. That's what physics does, is it teaches us, it forces all of us how to get smarter. And what that means is physics is trying to teach you what to do when you don't know what to do, right? Knowing what to do when you know what to do, you don't need anybody for. What you need to know is what to do when you don't know what to do. And I'm telling you that what that is the steps. And you see that you start practicing it like when you already do know what to do. So notice a couple of subtleties. Number one, this problem was only one teeny bit harder than the other one, but already it's just hard enough that I'm starting the strategy of I'm rearranging the algebra, doing everything I can before I plug in any numbers. Many of you could have just plugged the numbers in right away. I know that. You could have just said, you could have just put negative 30 on the left side and zero point 0.3 equals zero point 0.3 times A and just sort of seen it and solved for A. But I'm saying a good practice as things get harder is do all the algebra or the calculus or the trigonometry first and plug in the numbers at the last. And this is a pro tip, like write it down if I'm not writing it down. Plug in the numbers last because first of all, physics is going to have less and less numbers in it as you go along. You want to start really getting used to thinking without the numbers. The numbers are just the specific details of a specific example. They're not really the physics relationship. Second of all, if you happen to make mistakes on your calculator or something like that, you don't want it to bleed through all the work. So just leave the numbers for last, as I've done here. That's pro tip number one. Number two, notice I'm getting all hot and bothered about like it's F net equals MA in step three. And then in step four, eventually we divide both sides and say A equals F over M or whatever. Why am I making a big point about that? Because again, and I said this in another class, it seems to make an impression on people. I'm telling you from experience, and I'm telling you, I hope it's clear. Some of you know, I love physics. I've been doing physics for a long, long time. I've been teaching physics for a long, long time. It is not because I was born good at it. It was hard for me in college. I want you to know that. I got some really bad grades. In fact, whatever, that's a whole other story. Believe me, I've gotten bad grades in physics, certainly in undergrad, even in graduate school. And I struggled, not always, but a lot of the time. It's not that I just get it. It's that I worked at it like you're working at it. And some of you, and frankly, some of you do get it much faster than I ever did or ever do. I've just been doing it for a long time. So I'm telling you from the benefit from experience that what I used to do all the time, if I was stressing in the middle of a homework assignment or an exam, if I was getting anxious, what I unconsciously would do under time pressure, and I think a lot of people do this, what I would unconsciously do is scramble to come up with something relevant. Like if they asked me a question, I didn't know what to do. I'd like write down something that seemed relevant, like, oh, okay, I'm looking for A, but I have F. All right, I guess A equals F over M. I would write down something relevant, and then I would do a bunch of math to try to make it true and get a true, correct answer. Unconsciously, I didn't think of it that way, but that's what I was doing. And it seems totally reasonable. Write something relevant and then make sure your answer is true. But what I'm secretly telling you after experience is actually, if you stop and flip that script, if you are getting stressed or anxious about the difficulty of a problem, the real physicist way is to not do that, is to always start by writing something that's true and then do the math to make it relevant. That's a big subtle distinction that if you start getting, so you just write down things that are just true. First, we write down F net equals MA because it's freaking true and everybody knows it's true. And you're getting points for writing it down. In other words, you write down F net equals MA even before you're completely confident that you know what you're going to do with it. If it seems remotely topical, if it's because you know you've got force and you're solving for acceleration, so you know the law you're looking for has to relate to both, write the law down in its true full form. And then start manipulating to make it true, to make it relevant. Sorry, because even if you screw up, you're at least getting credit for the truth, and also you can build off truth. You can't build toward truth. Okay, I've got 3 minutes left. I still would actually like to let you go early, but last pro tip, since you've been so patient and we've gone through 2 exercises now, and I think you get the point. For the rest of the exercise, I'm going to tell you right now. For step 3, I'm sorry, for question 3 on the homework, again, it's the same. It's another acceleration question. You're going to use the same procedure, only you're going to a different place. You're just going to plug in different values for step 3. For question 3. Question 4 and 5, I'm telling you right now, the pro tip is that the step 3 that you're going to want to do for questions 4 and 5 of this homework, you're going to want to think about energy conservation, whether it's work and energy, depending on what professor you had or how you think about it or what resources you find online. You're either thinking the work kinetic energy theorem or kinetic and potential energy. Like that's the way you need to think for question 4 and question 5. It'll be the same procedure for both, but the answer will be a little bit harder to get for question 5, but it's the same procedure. It's energy conservation, but I'm warning you now for step 3, write down a statement that is true, always true, such as for any system where all the forces doing work on the system are conservative, the total amount of mechanical energy is a constant. Something like that. Like that is actually correct. Like if you caught that, quark bless America. Something like that is what you're saying for step 3 of questions 4 and 5. Something about energy conservation, and then make it narrower and narrower to fit the particularities of kinetic or spring potential or whatever you're using there. Okay. We still have one. Questions 7 and 8 are harder to apply the 5-step method, but you still can. If you think a certain step is not applicable, just write this up and say not applicable. Okay, but acknowledge it. Question 9 is where you're really gonna have to think. If you have to give up in the middle of question 9, I understand, and I'll just go as far as you can and be honest about it. Do not just copy things off the web and just write them down. You'll have time to revise and get a perfect score later if you get solidly into question 9. Okay, that's class. So, wait, no, I don't mean to be calling you out. Oh, sorry. Oh, I hope I'm not. Okay, well, I'm done. You can go. But if you have any questions, you can stay and ask questions. But I hope I didn't offend tree. Wait, sorry. Okay. Okay, wait. All right, so we're done. I'm going to stop the recording. I'm going to hang up. I actually also do have to go. I'm going to hang up for a second if there are any quick questions. But if they're long, I might have to make an appointment for later. And I hope I didn't offend Tree or anybody with. I hope I was joking and he was joking. I'm not sure, but okay. Recording.